Thanks. Well, here I go. I guess I should start with a word of thanks to my employer, Enterprise DB, for allowing me to be here today and for paying for me to be here today. There have actually been a lot of performance and scalability enhancements in PostgreSQL 9.2 that a lot of different people have worked on. I'm one of those people, and I was involved in a good number of them, but there are, and I blogged ferociously about them, but there were actually a lot of other people who did really good things too. So today I'd like to take you through some of those changes. I tried to kind of group the improvements that we have in PostgreSQL 9.2 into areas. And as you can see, that was a little bit difficult because there's a lot of areas. But I think the two things that people are probably most excited about or most aware of are some changes in the area of high concurrency, particularly what happens when you have servers running PostgreSQL that have a very large number of CPU cores, and also index-only scans, which provide an ability that PostgreSQL has not had in the past, which is to answer queries by providing data directly from the index without having to access the underlying table. But in addition to those two areas, which are maybe the really sort of big whiz-bango things, there are a number of other things which actually can be very significant. Parametrized plans, some indexing improvements, sorting, power consumption, and some miscellaneous improvements. Although those things haven't, I think, gotten quite as much PR, there's actually some really cool stuff in there, so I'd like to take you through some of those improvements as well. This is a graph that I made about a year ago now when I was working on some improvements to the PostgreSQL lock manager. What this is showing us is a completely read-only workload involving lots and lots of short queries, single select statements doing primary key lookups on a database that was small enough that it fit inside shared buffers. And the blue line down toward the bottom is what happens when you do this on PostgreSQL 9.1 on this 32-core AMD Opteron system. I committed a patch to PostgreSQL 9.1 that implements a sort of a fast path locking mechanism for certain types of locks that are frequently taken but rarely conflict. And that got performance to go up from the blue line to the green line, which was good. And then we did some further optimizations, and we got performance to go up to the red line, which was better. One thing that's kind of interesting to note here is if you look at the blue line, it is low, but it has one pretty significant thing going for it, which is that at least it's flat. And you laugh, but look at that green line. It looks really good compared to the blue line, but you can see it's slanting down pretty sharply as you get toward the right side of the graph. The reason why the reason why those top two lines flatten out at around 32 cores is because this is a system with 32 cores. Right? So we can't really expect to get any scaling beyond 32 cores. But what we don't want is we don't want a degradation, or at least we want to minimize the degradation as we further ramp up the number of clients. And with the initial patch that I committed, that was a pretty serious problem. In fact, there were some people who reported that the green line actually dropped below the blue line. The initial patch, they actually took this graph on their hardware far enough out to the right side that the green line actually crossed the blue line, and they were seeing worse performance with this performance improvement than they had been seeing before. Obviously, if you hit it in the sweet spot, it was great. But some of the work that we did after that was just to squeeze a little bit more out of the initial optimization. But the other thing that we had to try to do was get rid of that regression. And as you can see, we were pretty successful in doing that. That red line is still maybe declining a little bit as you creep out there toward the right side of the graph, but not too much. since we made that second round of fixes, we have not had, fortunately, any more complaints about performance regressions as a result of this patch. So this is really cool. I was excited about this. This is a great graph to be able to put up and say, hey, look, I did that. But in the interest of fairness, one thing to keep in mind here is Postgres 9.1 doesn't suck in general. The thing that's making it suck on this particular workload is the fact that the queries were the simplest imaginable SQL statement. So if you have that workload and you have a lot of CPU cores, you are going to see this tremendous benefit with PostgreSQL9 too. But a lot of people are running more complex queries than this, queries that go on for more than a millisecond. And those people are not going to see this huge benefit because they were already getting this benefit. What we were really eliminating here is some of the overhead of accessing a table for the first time within a single transaction. And so when you're running very, very short transactions that are one SQL statement, you pay that overhead a large number of times. But if you have longer running transactions, either a query that just runs for more than a tiny fraction of a second or a multi-statement transaction that accesses the same tables repeatedly, you're not going to see this profile. Yeah, so I've kind of already talked through this slide a little bit here, but this is basically what we did, what we did in order to make this happen. The first thing up here, adding a fast path to the lock manager to allow weak relation locks to bypass the main lock manager in most cases. That was what got us up from the blue line to the green line. And then the remaining two optimizations up here were what we did to get it up to the red line. And the thing that was primarily responsible for fixing that negative slope of the green line as you moved out toward the far end of the graph was that third one, wait-free test for new shared invalidation messages. Lock-free and wait-free programming is still really in its infancy in the PostgreSQL code base. We rely on locks for a lot of things. And the way that doesn't stink too badly for performance is that we've done a very good job holding those locks for very brief periods of time in most cases. And we've made the locking primitives themselves very lightweight so that it doesn't take a long time to acquire or release a lock. We've even experimented with trying to make the lock, acquire, and release primitives even faster than they already are. But that proved to be a fruitless line of investigation because they're already so well optimized that making them faster just doesn't buy anything material. As we are moving out into systems that have larger and larger number of cores, 32 cores, 64 cores, and I'm sure eventually we'll see 128 and 256 core systems become more common, we're going to have to look harder and harder at some of these techniques that people have developed in other systems that do scale to a gigantic number of CPU cores to keep pace with the pack. So I said 32 cores. We had linear scalability out to 32 cores. And then I discovered in about April that with all of the changes that we've made out to that time, which included the changes on the previous slide plus a few more things, we could actually scale pretty much linearly out to 64 cores. So this is a machine with 8 AMD 6272 processors, each of which had 8 cores. Both this machine and the one that was used to generate the previous graph were provided to me by Nate Boley through the PostgreSQL community for the purpose of advancing this work. It's pretty sweet. Technically, it's not quite linear scalability because the number at 64 cores works out to be like 63 3/4 times the single core output. So it's not quite 64, but I think it's close enough for government work. One of the other interesting things that you can see on this graph is that there's kind of a funny bend in the curve in that 16 to 24 core range there, where it doesn't seem to be going up very fast anymore, and then all of a sudden the slope of the line changes and it starts shooting up really quickly. People see what I'm talking about there? Yeah. Why don't you fix that problem, PostgreSQL developer people? Well, it turns out this isn't our bug. This is a Linux problem. If you do this on a BSD system, that doesn't exist. You get some other problems because it turns out their kernel has high concurrency bugs too, but you don't hit this one. That trough between, on other graphs I've seen it around, I think if you look at the previous graph, it actually happens a little lower, maybe in the 12 to 24 range. Here it's more like 16 to 28 or something like that. But there seems to be some kind of Linux problem, which I'm guessing is a scheduler bug, where if you run anything, any process at all, with about this many current threads and measure how much work it's getting done, you see this kind of thing where it's scaling sublinearly, and then as you get out to 32 cores, it suddenly shoots up and makes up all of its lost ground and gets back to linear. I actually can't explain why this is happening because I don't know the internals of Linux well enough. But Greg Smith was actually the one who turned me on to the fact that this was not something that was part of PostgreSQL, because he'd actually seen it on completely different tests that had nothing to do with PostgreSQL on Linux systems. And a couple of FreeBSD guys provided me with graphs of what it looked like on their system. So I think at this point there's enough evidence to conclusively say that that weird shape there is not our fault. We also did a lot of work this release on improving write concurrency as well as read concurrency. I found out, somewhat to my chagrin, that write concurrency is a much harder problem than read concurrency. There's a lot more, at least in PostgreSQL, there's a lot more locks involved. And the other thing that makes it more difficult to work in this area is that the benchmarks are much less repeatable. I mean, you can test the read concurrency with 5-minute benchmarks pretty easily, and actually I think you can go down to like 30-second benchmarks and get pretty much the same answers. With write concurrency, I had to do half-hour test runs, do 3 of them, take the middle of the 3 results, and even then sometimes things bounced around a little. So that made it harder. Plus there were more locks involved and more moving parts. We have a lot of optimizations to skip certain parts of query processing when we're doing a read-only query. So there's a lot of issues that just don't come into play on the read-only queries. So the write concurrency is a harder problem, but we were able to make some pretty good progress despite that. A colleague of mine, Pavan, who was working at EDB at the time, had this idea that maybe if we took some of the very frequently accessed members of the pgproc data structure, which is a very important data structure that PostgreSQL uses to track currently running transactions. He said, maybe if we take some of the very frequently accessed, very high traffic members of that data structure and put them in a separate data structure instead of having them incorporated into one big data structure, we'll get a performance improvement. And I said, that is the stupidest idea that I've ever heard of in my life. Please don't even pursue that. There's no chance of that gaining anything material. It works great. It's the biggest thing we did this release for write concurrency, probably. So it turns out, I now know, cache line passing is amazingly expensive. The number, when you have multiple CPUs accessing the same data, it doesn't move around the individual bytes of memory. It moves around chunks of bytes of memory. And so if you, and it turns out that there's just not enough memory bandwidth on modern CPUs to satiate the demands of something like PostgreSQL. So, if you have this big data structure that is mostly not being concurrently accessed, but parts of it are being accessed with a high degree of concurrency, you end up moving around the entire data structure from one CPU to another CPU every time there's concurrent access. If you instead segregate the frequently accessed data and put it in its own data structure, then you end up greatly reducing the amount of memory contents that has to be moved around between one CPU and another CPU. And the CPUs are so much faster at executing instructions than they are at moving memory cache lines around that turns out to be a pretty significant win. Now, there's a couple of other things we did as well. I noticed I was testing with synchronous commit turned off, or in other words, with asynchronous commit turned on, which a lot of people don't run that way. Some people who don't run that way probably should, because it's a great performance optimization if you can afford to lose a second or two of transactions in the event of a system crash. But that's what I was testing with, because I didn't have a great subsystem, a great disk subsystem on the machine I was using for testing purposes. And what I noticed was that if I cranked down the wall writer delay, I could get a significant performance improvement. And so I reported this on the list, and Simon Riggs said, hey, I happen to have been working on a patch that improves the responsiveness of the wall writer. Why don't you test it out and see how it works? It worked very well. So we got a nice little benefit for write traffic there if you are running with async commit. We also made some changes to the C-log machine rate. C-log is the commit log. It stores data about the status of committed transactions, and it gets really, really hot when you have a lot of write transactions in your system, because this C-log data structure has to be updated every time a transaction commits. And if you're running a lot of very short duration write transactions, then this data structure gets updated a lot. It also gets accessed a lot because it's part of our multi-version concurrency control, or MVCC implementation, and so people are reading data from it all the time. The code is fairly old. It's basically kind of just worked for a long time, and it hasn't had a lot of love, so I think there are some more improvements to squeeze out of it. But we were able to do a couple of simple things which did help quite a bit. One is that we increased the number of C-log buffers from 8 out to 32, so we can keep more of the C-log data in cache. We also fixed the SLRU buffer replacement algorithm, which was actually kind of buggy before. It would have a tendency to decide, oh, this buffer here needs to be evicted because it hasn't been used recently enough. And then what would happen is basically every transaction in the entire system would start waiting for that buffer eviction to finish for no particularly good reason. And so the biggest effect of it was on latency. You would get these latency spikes on a very busy system. Evicting the buffer was slow because you had to wait for the buffer to be written all the way down to the disk. And now instead of having one guy do that and he gets delayed, everybody would decide to wait for that to be done. And so everybody would get delayed. And it was actually a very easy bug to fix. It was just a couple line code change once you actually understood that this was happening. But it wasn't at all obvious from reading the code that it would end up having this behavior. And so it took a lot of instrumentation and testing to figure out, where are these latency spikes coming from? And then when I finally found it, I'm like, oh, really? Then after that, it was a pretty quick fix. Another thing we did, which had a small impact, is we discovered that there were certain cases where index scans were actually looking up every transaction ID that they needed to know the status of twice in C-log instead of only once. So we were able to make a significant reduction in the volume of accesses to C-log by avoiding that double lookup. Peter Gagan did some work, and Heikki Linnakangas also did some work to improve the piggybacking of wall flush, which results in better group commit behavior. We've technically had group commit behavior for a very long time in PostgreSQL, but these changes made it work a lot better. So if you're running with synchronous commit turned on, this can have a significant impact on your throughput, especially if you have very, very, very small transactions, like you're inserting one row at a time and then committing the transaction. Now, another option is you might not actually want to do it that way because that's really inefficient. But there are definitely cases where you'll see a significant performance benefit from this. And it even helps on PG Bench workloads, although not nearly as much as if you pick the best case for the optimization. And finally, Heikki also did some work to reduce the volume of wall generated by copy. And the big effect of this is that if you have several people doing big copies into the database at the same time, that now scales much better than it did before. So it's easier to do concurrent data loads and have that actually work out well than it was previously. So I don't have graphs showing all of these, but I do have a few graphs. This is a PG bench graph. I did it in February of this year. So a little bit has changed since then, but not too much. The green line is PG9.1, and the red line is PG9.2, current as of that date. And you can see that it's definitely not scaling linearly out to 32, which was the number of cores that we had here. But it is better. It's scaling linearly out to 24, which it wasn't before. And 32 is equal to 24 instead of being less. So there's more work to do there, obviously, to really get that to scale linearly. And maybe some of that will happen in time for Postgres 9.3. But it's still a nice improvement. The commit scalability is pretty dramatic. This is sort of a best case test that Peter Gagan put together for his patch to improve the group commit behavior. You can see that what happened before in Postgres 9.1, which is the green line, is that basically you just couldn't get more than about, I guess that's about 1,650 commits per second on a trivial insert statement under Postgres 9.1 because it just bottlenecked on locking after that. And by jiggering with the locking and introducing some more efficient primitives, we were able to get that to go, Heikki and Peter were able to get that to go much higher. And you can see on the hardware that I tested this on, which is not a great disk subsystem, it gets up to close to 13,000 commits per second out at the 250 client number, which is very nice. Okay. That's all I have to say about CPU scalability. Let me just pause briefly before I go on to index-only scans and ask if anybody has any questions about that, any stuff before I move on to the next part. Is there anyone who is still awake after the first part? Okay. So index-only scans. As I think many of you probably are aware, some of you may be painfully aware, earlier releases of PostgreSQL did not have the ability to answer a query using only the index. Even if you were using an index scan, you also had to look at the table. And there was a good reason for that. It wasn't just a trivial oversight in the code someplace. The reason is because a row could still have an index entry, but actually have been recently deleted in the table. So if you just looked at the index, you would say, oh, there's a row there. Well, actually, no, there's not a row there anymore. It's recently been deleted. You wouldn't actually know that without looking through the index and down into the table. The old index entries are removed by vacuum, and vacuum is an operation in PostgreSQL that only happens periodically, not instantaneously when you make a change. So you get wrong answers. So we needed a way to get around that. And we got there using something called the visibility map. Heikki Linnakangas first implemented the visibility map in 8.4. And the reason he initially did it was to make vacuum more efficient. And it was pretty successful at doing that. If you are one of the unfortunate people still running a pre-8.4 release and you hate your life because vacuum sucks, you may wish to consider an upgrade, because I'm certainly not going to claim that vacuum is perfect in newer versions, but the 8.3 to 8.4 jump is actually pretty huge as far as reducing the amount of pain that's associated with vacuum. Unfortunately, not eliminating it, but it is a lot better. So the visibility map basically stores one bit per table page, and that bit can only be set if every tuple on that page is visible to all current and future transactions. And so if, for example, a row on that page is updated or deleted, then the bit gets cleared. So that potentially provides a way to do index-only scans. We can look at this visibility map, which is very small and fits easily in memory, even if the table doesn't, and we can say, oh, well, all the tuples on this page are visible, so we know none of them have been recently deleted or updated or inserted, so we're going to be able to see them all definitely. We don't really need to look at the page if the columns that we need are available from the index. However, That optimization wasn't implemented until 9.2 because in earlier versions, the visibility map was kind of like a hint for vacuum. And a hint is another way of saying it might be wrong. The visibility map in older versions was not crash safe. And so it was okay to rely on that for vacuum, which is just a garbage collection process. And if we have a crash and we leave a little garbage behind, it's okay. We'll clean it up eventually. But it's not okay to tell people, well, eventually your queries will give correct answers, but right now they don't. So that was kind of a non-starter. In 9.2, I wrote some code that turned out to be a lot harder than I thought it was going to be to make the visibility map crash safe. And after a couple of rounds of fixing stupid mistakes that other people were kind enough to point out to me, we actually got to the point where we think it is crash safe. And then after that, Ibrar Ahmed from Enterprise DB and I wrote the code to do the initial implementation of index-only scans. And that Tom Lane committed that and then made it a lot better and added a whole bunch more features. So we now have index-only scans. So why do you care? Are they good? Do they make things faster? Yeah, if you have the right workload, they make things faster. Here's the test I did. I used my MacBook Pro, not actually this one because the one I used for this test died, but my old MacBook Pro. I'd had 4 gigabytes of RAM. I had shared buffer set to 400 megabytes. I made a really big pgbench instance initialized with scale factor 1,000, so it did not fit in the memory on this machine. And then I ran a select-only pgbench test for 5 minutes with 8 concurrent clients, and that's just doing primary key lookups over and over and over, single-statement transactions, just doing primary key lookups. So I got the results of that test. And then I created an additional index on the pgbench accounts table. The pgbench accounts table has a primary key index, which is on the AID column. And I added a second index, which was on the AID column and also the A balance column. The pgbench accounts table in this test worked out to about 13 gigabytes. I discovered that the two indexes were exactly the same size, apparently because there were some padding bytes in the original index that got filled up in my covering index with useful information. So those were both about 2 gigabytes, and here are the results. And with the default pgbench configuration, I got about 63 transactions per second. With the covering index, I got about 300 transactions per second, so almost a factor of 5 speed up. I've seen speed ups on index-only scans ranging from no speed up at all to 700 times faster. This is a sort of middle-of-the-road case where it works out to be about 5 times faster. Now here's an optimization that I think, am I missing a slide there? Oh, I am. Well, that's okay. So Tom Lane did some great work on implementing something called parametrized plans. And a parametrized plan is one of those features that people go, what the heck does that mean? Well, it means that if you've got a certain kind of query, it's going to go like a gazillion times faster than it did before because now the planner is smarter. So I've got an example here, and the example is a little artificial, but basically what I have is I have a left join between a small table and another join. And the other join is a join of 2 really big tables. So it's a fairly specific set of circumstances, right? You need a little table, left join, 2 big tables. And in this case, for my big table, I used the giant pgbench database that I had left over from the previous test. And for my little table, I just used generate series call, which generates the numbers from 1 through 10. What you don't want to happen here is you don't want to join the great big tables first, because that's really hard, and then join to the little table afterwards and throw most of that join product away. But in fact, in 9.1 and earlier releases, that's exactly what we were doing. In 9.2, we can actually do the joins in the right order. So you see here there's a tremendous performance improvement. On 9.1, it took a little over 4 minutes to execute this query. The first repetition was 246 seconds, and then 250, and then 251. On 9.2 devel, the first time I executed the query, it took 579 milliseconds, so 500 times faster. And then each subsequent execution was like 500 times faster than that, because the data after that was now cached and all in RAM. Um, so, if that's not enough of a performance gain to impress you, then you're a tough crowd. Again, not everybody's going to have the workload where they can benefit from this. But even in our regression tests, Tom Lane found a number of cases where his work on this actually delivered significantly better plans than the ones that we had before. The regression tests run in like 30 seconds, so it doesn't really matter. But I think that is a good indication that there are actually people out there who are going to benefit from this in real-world query situations. And this kind of pattern with the big joins under the left join is what to look for. So here's the plan. You see in 9.1, we start by joining the two gigantic tables with a merge join. And then we do another merge join to the little table, and it's slow. And then in 9.2, we get a much better plan. We are essentially doing the join between the big tables 10 times instead of 1 time. But each time we do it, we only pull out 1 row from each of the big tables. So instead of joining 1,000,000 rows to 1,000,000 rows, or I think it's actually 10 million, instead of joining 10 million rows to 10 million rows 1 time, we join 1 row to 1 row 10 times, which is a lot better because the total number of rows we join is 10 instead of 10 million. That's why it's a lot faster. Indexing. There's a bunch of indexing improvements in 9.2. One of them is if you have an indexed column, and say you have something like foo equals any array, and then you have a bunch of values in the array. In older releases, what you will get is you will get a bitmap index scan. As of 9.2, it is possible that you will get a plain index scan. If you are not familiar with the difference between bitmap index scans and plain index scans, wow, that's really noisy. If you're not familiar with the difference between bitmap index scans and plain index scans, in general, bitmap index scans are very, very awesome and improve the performance of tons of queries. However, having the option to do a plain index scan for this particular type of query is actually quite useful if you happen to have these kinds of query, because when an index scan is retrieving very small number of rows, like 0 or 1, which are actually pretty common special cases in database work due to things like primary keys and foreign keys. We see 0 rows and 1 row a lot. There's actually a tremendous performance benefit for queries of this type in being able to use a plain index scan when you're only retrieving a small number of rows. And there's a bunch of indexing improvements related mostly to spatial data types. The less than at, greater than at, and operators are contains, contained by, and overlaps with. So obviously these operators don't come up for strings, right? They come up for geometric data types. But what's been done is some work, I believe, by Alexander Kortkov to make the query planner smarter about estimating the number of rows that will be returned when you use those operators. And that turns out to be really important because the whole way that the query planner operates is based on the idea that you're going to get row count estimations. And if you take your explain analyze of a problematic query and show it to a PostgreSQL guru and say, why is my query plan slow? The first thing they're going to say is, oh, your selectivity estimates are way off. And you're going to say, well, what do I do about that? Well, sometimes there are things you can do about that, but it's a lot better if the system just gets them right for you. So there's been some improvements there. Gist indexes have also been improved, particularly the way we build gist indexes. A gist index is a spatial index. The regular kinds of indexes that we think about are B-tree indexes. And in a B-tree index, you can basically just do equality, less than, greater than, less than or equal to, greater than or equal to. So a B-tree index is basically just taking your data and sorting it for you, and then letting you pull out pieces of data based on where that data appears in the sort order. That's useful. But if you have points or boxes in a 2 or 3 or more dimensional space, it doesn't necessarily help you very much because you don't have this ability to take all of your boxes that are in different places in a 2-dimensional plane and put them in some kind of sorted order, right? You want to ask questions about, is a box above another box or below another box, to the left of a box, to the right of a box, overlapping with a box, containing a box, being contained by a box. There's lots of possibilities, and the neat thing about gist indexes is that they allow you to answer all of those kinds of spatial questions with a single index instead of having to create multiple indexes for every different question that you want to be able to answer efficiently. But it turns out spatial indexing is really complicated because it's hard to figure out when you're building this index exactly which parts of the data you should put in which parts of the index. When you're just building a B-tree index, it's pretty obvious. You just sort the data. You put it in order. There's only one way to do it. But gist indexes, there's more than one way to do it. And depending on which way you do it, it can affect both the build time of the index and also the index quality, which means how fast are we able to actually answer queries using this index. Alexander Kortkopf, again, did some work to make indexes build more quickly and also to have better index quality so that queries can subsequently be answered more quickly. So that's pretty cool. We also have a whole new type of index. In older releases of PostgreSQL, we have B-tree indexes, which are, again, are the traditional kind. Gist and GIN indexes, which are used for spatial applications as well as full-text search. And hash indexes, which nobody uses because they aren't any better than B-tree indexes, and they get corrupted if the system crashes because we never really got around to fully supporting hash indexes. Maybe that will get fixed someday, but it isn't fixed yet. In 9.2, we're getting a whole new type of index, SPGIST indexes. And these are a more specialized type of index. They are, again, like GIST and GIN, they are primarily for spatial data with some application to full-text search. Or I guess I should say text search, not full-text search in the case of SPGIST. Basically, the difference is that SPGIST indexes are optimized for, I guess the easiest way to think about it is they're optimized for points. If you're trying to index something like a box or a polygon that has an extent to it, that it takes up space in some abstract plane, you still have to use GIST and GIN indexes for those. But if you're indexing points, you now have an additional option, which is SPGIST. And in theory, this is much better in all kinds of really important ways that not being a spatial guy, I can't tell you about. Yeah, I think this is still a little bit new technology, but there are some very promising benchmark results that Oleg and Theodore, who are the authors of this feature, have done. But I'm not going to go through it in detail because I don't fully understand it. You're saying the first case there affects in clauses as well. I don't know whether that's true, but it is very possible that it's true. Yeah, so you confirm that it also works for in. Okay, so maybe this also affects a in 1357. That's what people seem to be telling me. I actually have not verified that case, but I'm totally willing to believe that you have. Sorting. This is work that was really led by Peter Gagan, and then a couple of the rest of us poked our nose into it and hacked up his patch, which he was very gracious about. But PostgreSQL is a very extensible system. You can create new types. You can create new operators, which is really cool. And most of the time is fine from a performance standpoint of view. But there are occasional situations where it's not fine. And one of them is sorting. Because you can define your own operator, that means, in effect, that you can define your own sort order, because you define a less than operator, in effect. And you define what it means for one thing to be less than another thing. So now you've got user-defined code defining the meaning of less than. And that means that when someone then says order by, they are using your less than operator. Now, most people don't do this, but some people do this. And what it means is that not only for user-defined types, but also for built-in types, we have a very general and flexible mechanism for invoking whatever the appropriate less than operator is for the data type that you're trying to sort. And what we discovered, what really Peter discovered, is that we were doing a lot of repetitive work in the process of calling that generic user-defined code, even when that generic user-defined code was doing something incredibly simple, like comparing two integers, which takes one machine language instruction. We were actually doing it in a way that made it take 30 machine language instructions instead of one. Now, the good news is that modern CPUs are really good at pipelining instructions and predicting branches and doing all of these other kinds of things that mean that sometimes you can have 30 instructions instead of one, and it still doesn't perform that much worse than if you only had one instruction. But it's not completely free, for sure. And so what we found is that we were able to introduce something called a sort support infrastructure that allows us to skip a lot of the repetitive argument packing and unpacking that was happening inside the sorting code. And that improved the performance of sorting of small amounts of data pretty noticeably. We also introduced a specialized version of QSort, the quicksort code, which turned out to be significantly more efficient than a general QSort because it knew the exact sizes of the objects that it was sorting when it was sorting tuple pointers. And that made a surprisingly large difference when sorting data in memory. Power consumption. I wasn't sure whether to include this in a performance talk, but I thought it's cool, so maybe I'll include it. Again, this work was driven by Peter, and there's a utility called PowerTop that you can use on Linux to measure the number of times that the CPU is waking up every second. It turns out that when the CPU doesn't have anything to do, it very, very quickly goes into lower and lower power states. And if you are running enormous numbers of servers, then you really care about the number of wake-ups that you have. Or if you're running a laptop and it has a battery in it, and the battery can only hold so much electricity before your computer goes dead, that might be another reason why you would care about how many times the CPU was getting kicked up into active mode again and starting to consume more power. And I had no idea of any of this, but it turns out the way people usually measure this is how many wake-ups per second are happening. Less is better. In 9.1, there's about 11.5 auxiliary process wake-ups per second in a configuration where you're not using any replication. And that's a lot, especially if you're a hosting company and you're running hundreds of thousands of copies of PostgreSQL, and they're all doing 11.5 wake-ups per second, and most of your users are flakes and they're not really using the service anyway, so you're just like wasting a lot of power. So in 9.2, the PostgreSQL can kind of notice that nothing's happening, and it will gradually shift into a lower power state where the number of auxiliary process wake-ups per second will ratchet down and down and down until it gets down to eventually 0.4 auxiliary process wake-ups per second on a system that's been idle for a couple of minutes. So I don't know how many people this is going to help, but it's pretty cool because like 11.5 is a lot bigger than 0.4. And so if you have a system that's running PostgreSQL and you run PowerTop on it, you no longer see PostgreSQL shoot to the very top of the things that are waking up the CPU. It's like down somewhere in the middle of all the device drivers and other crap that's running on the machine. So that's kind of nice. I think eventually we'll have to do some more work in this area if we want to not be the nail that's sticking up. One of the remaining issues is that if you are running a replication configuration, we have not done all of the work to make that as power efficient as a non-replicated configuration. So you will still get these numbers won't look as good if you're running replication. You're still going to see a reduction, but you're going to have an uncomfortably high number of wake-ups per second again. And of course, eventually, Red Hat, it turns out, I found out from Tom Lane, Red Hat is going around and yelling at everyone who has a high number of wake-ups per second compared to other things on the system. So eventually, other people who are also getting yelled at are going to fix their stuff to make their numbers of wake-ups per second go down, and we're going to end up back at the top of the list, and then people are going to start yelling at Tom again, which is probably about when this number is going to start really going down again. So yeah, there's a possibility here for real cost savings. Some other improvements. We have a new plan cache rewrite. Tom Lade did this work. Many PostgreSQL people will tell you that you have to approach prepared queries using a little bit of caution, because well, I shouldn't say existing since 9.2 is out now, but in older releases of PostgreSQL, if you use prepared queries, you get one query plan, and you get that query plan the first time you execute the prepared query, and then you just stick with it forever. And sometimes you need different query plans depending on the values of the parameters that you're executing the prepared query with. And so then you're sad. And so Tom rewrote this so that it'll replan it a couple of times and see if the plan seems to be staying the same or changing. And if it seems to be changing, then it'll keep replanning it every time. If it seems to be staying the same, then eventually it'll stop and just settle on one plan. Not really sure this is going to fix all the problems in this area, but it should help. We got a userspace access vector cache for sepgsql. This is a performance improvement if you're using security enhanced Linux with PostgreSQL. Faster array assignment in PLPGSQL due to caching of type information. This was Pavel Stahel, I think, did that work, and Kai-Guy Kohai did the last one. And an improved spin lock implementation on the HP Itanium. I discovered that the manual said one thing about how to do spin locks on HP Itanium, and what we did was a different thing than what the manual said. And our invention did not work as well as the thing that was in the manual, so we corrected that. So a few lessons learned. I got to go quickly here because I'm just about out of time. But some things I learned while working on performance that may or may not be useful to you if you work on performance in the future or you're just curious. pgbench is a pretty good test. Beating on the database doesn't answer every question, because in real life people don't always beat on their databases. But it's just a really simple test where you beat on your database and see what happens. It's pretty good for flushing out a lot of problems. As I said earlier, you got to run the right test for at least half an hour. 5 minutes is plenty for reads. You got to watch out for outliers. So run each test 3 times and take the middle value. Transactions per second is pretty much constant throughout the duration of the test for read-only tests. But for write tests, it shoots up and down based on the checkpoint cycle is one part of it, but there's a whole bunch of other effects as well, including the C-log behavior and SLRU behavior and probably some other things that I haven't figured out yet. So when you're doing write tests, it's actually really important to not just look at whether the number of transactions per second went up, but how it changed in each time interval over the course of the test. Because maybe you made it better for some parts of the test, but you made it worse for other parts of the test. And if you look at an average value, as I was doing until Simon told me I was an idiot, then you will not really understand what's going on. Actually, he said it nicer than that, but I was being an idiot. There's a compile time flag called LWLockstats that's really helpful. I'm not sure if I've got it committed yet, but I'm actually working on an enhancement to that to make it show more information about spin lock contention, which is a real problem for some of our locks that are taken frequently, but in read-only mode. If you want to do CPU profiling, do not use gprof because it sucks. And do not use oprofile either because it's much better than gprof, and it still sucks, which gives you an idea of just how bad gprof is. I mean, the overhead of gprof is something like the size of the planet Jupiter, and the overhead of oprofile is like the size of a mountain, which is better, a lot better, but still way too much. Perf is got way, way better performance characteristics than either of those things. The overhead is quite small. You can actually use perf not only to measure CPU time, but to measure context switching. And you can actually get a call graph and see exactly which parts of the code are causing context switching. And that tells you where your LW lock contention is coming from, which is how I found the problem where we had double C-log lookups for each index tuple we scanned. Custom instrumentation is awesome. I have so many throwaway patches that never have any hope of being committed to the main tray, where I like hacked things up so that it printed out and told me where things were taking a long time or which parts of a function were slow. And it's just way better than any of the things you can do with the profilers, because you can get it to tell you exactly what you want to know. Extreme workloads are good because they exacerbate bottlenecks, which makes it easier to judge whether you've actually solved the problem. It takes a long time to understand what the problems really are. And it's a good idea to measure the system performance in a lot of different ways. Look at TPS, but also look at latency, how often your locks are being contended, how long you wait when the lock is contended. You kind of find different problems in each area that all sort of contribute to the performance. Unfortunately, I don't really have time to talk through exactly what LW locks are, but basically they're a read mode, write mode lock, shared exclusive, that's used to protect shared memory data structures. And it's sort of becoming increasingly clear. We rely on these all over in the code, but they're actually too simple for a lot of the things that we're using for, and we're kind of shoehorning our code into the mode that is supported by this locking mechanism that we have. It's not exactly clear what would be better than LW locks, but it is pretty clear to me at this point that there's a mismatch between what LW locks know how to do and the real synchronization needs in many parts of the code. So maybe we'll figure out a better set of primitives there at some point. Remaining problems, buffer replacement is mostly single-threaded. Your graphs won't look nearly as nice if your workload doesn't fit in shared buffers. So fitting your workload in shared buffers can give you a big performance boost. Wall insertion is single-threaded, particularly just after a checkpoint when you have lots of full-page writes. There's real scalability issues there. Fsync on a busy system can take like a lot of seconds to complete, like 10 or 30. And that's something we need to think harder about in terms of making sure that we're not doing Fsyncs while we're holding any locks that matter to anyone in the entire universe, because anytime we do that, it generates latency events. And my final point, more other things we fix. The worst proc array lock looks. That lock is taken by snapshot acquisition at the beginning of each query and by transaction commit at the end of each query. And the more other things we fix, proc array lock just sucks up all of the gains that we make anywhere else. The contention just all goes there. So at some point, we're going to have to figure out a better way to confront that. Pavon's changes definitely bought us some time in 9.2, but we're going to have to confront that issue at some point. That's all I got. I can probably take one or two questions, and then I'm going to have to take individual questions. Yeah? Have we been able to push the read-in memory workload to the point where it... have we been... Yeah, I have not been able to make a workload that fits in shared buffers, not scale linearly, because I don't have a computer with enough CPU cores to make that happen. 64, we're still okay. Probably if you go out to 128 or 256, or Stephen Frost was telling me today he had a system with 2 to the 14th power cores. Yeah, no kidding. 128 cores with 128 hardware threads on each core. It's a cray. So if you could actually run Postgres on a system with that kind of horsepower, I'm pretty sure you're going to see it does not scale linearly forever. I don't know, but I can't tell you what the inflection point is because I don't know. We don't have a big enough system. You will get a drop-off even at 32 cores or so if you have a workload that fits in memory but not in shared buffers. And that happens because of bottlenecks related to buffer eviction. So I think we might have to revisit our traditional advice about keeping shared buffers around 8 gigabytes, because if you can actually get your working set into shared buffers, there is a really big benefit to that if you have enough concurrent activity that it turns into a scalability problem. There's an old post on my blog that goes into this. It turns out it's not really a performance problem when we start thrashing shared buffers and going to the operating system cache. It's not that much slower in absolute terms, but it doesn't scale. So if you're doing that with a single concurrent query, whatever, it's 5% slower. But when you do it with a lot of concurrent queries at the same time, you get killed. Time's up. Sorry, but I'll be around afterwards if people want to ask questions. Thanks.